Hey everybody, welcome back. We are now talking about simple harmonic motion. Might sound like some weird words to you, but we'll describe what this is and this whole unit. Here we go. Alright, terms to know. So if we haven't really talked about much wave things or you haven't learned about that, this might be a little bit new, but it shouldn't be too difficult. Alright, so periodic motion, oscillation. Any kind of motion that repeats itself over and over. For example, a pendulum of a grandfather clock, vibrations produced by instruments, pistons in a car, waves, so on and so forth. Period. We kind of talked about period in the past with uniform circular motion, but it's the time to complete one cycle. So if something goes around, how long it took to go all the way around. If something is swinging, how long it took to go there and back. If something is pumping up and down, how long it goes to go up and down. Okay? Frequency is the number of cycles in a unit of time. Hertz. How many oscillations occur in 1 second. For example, if something is vibrating very quickly like this, it's how many times did it vibrate in 1 second. Okay, that's frequency. It's like the opposite of a period, but we'll talk more about that later. Amplitude is the maximum magnitude of displacement from the equilibrium. Okay, so for example, if something is going up and down like that, it's what is the furthest point that it reaches from this equilibrium state. Anyway, it could be a little bit confusing, but as we do the example problems, it should make more and more sense. A little bit of an example if you want to watch. Alright, some key things to know. So first, we're going to be talking about oscillations where there's a spring involved and a mass that's oscillating back and forth with a spring. So displacement is measured from the equilibrium point. So for example, in this case, how far it is from the equilibrium point, that's the point where if no forces are acting on it, that's the point where the net force is equal to 0. That's the equilibrium point. And in this case, the displacement is negative a because that's how far it is from the equilibrium point. This a symbolizes amplitude. Amplitude is the maximum displacement. So this is the furthest this block is going to be oscillating back and forth. Okay, it's the furthest point. A cycle is a full to and from motion, the same as one trip around a circle in uniform circular motion. Okay, so for example, if it starts here, it goes there and back. That's one cycle, not just there. That's not a cycle. There and back is one cycle. Period is the time required to complete one cycle, the same as period in uniform circular motion. I'm showing this uniform circular motion here because this topic has a lot more to do with uniform circular motion than it seems initially. Frequency is the number of cycles completed per second, the same as frequency in uniform circular motion. Okay, we talked a little bit about that already. Alright, so let's look at scenario A. Scenario A, force and acceleration is at a maximum to the right. Velocity is momentarily at 0. So you might be like, what? This block is all the way to the left. What are you talking about? The acceleration and the force is all the way to the right. So it's all the way to the left. We can see that it's a negative amplitude over here. And the reason why the force is all the way to the left, to the right, is because the spring is going to be pushing this all the way to the right. And whichever way the net force is, that's also where the net acceleration is going to be. Okay? And when this thing is going back and forth, it's going to momentarily come to a stop right before it turns around and starts going this way again. Okay, scenario B. Force and acceleration momentarily are 0. Objects at maximum velocity. So let's say it's moving from this part. It reaches this equilibrium point. That means there's no force, there's no net force acting on it, okay? For this moment in time, it's being pushed and pushed and pushed and pushed. And after it passes this equilibrium point, it's going to start getting pulled back by the spring going that way, okay? And before this equilibrium point, it's getting pushed to the right. But right at the equilibrium point, it's no longer being pushed or pulled at that moment. And So the force and acceleration is momentarily 0, and this is the moment where it goes the fastest. After this moment, it's going to be getting pulled back, so it's going to start slowing down. Scenario C, force and acceleration is at a maximum to the left. So it's all the way to the right. That means that the spring is pulling it to the left as much as possible, and it's accelerating to the left as much as possible. And since it's oscillating back and forth like this, this is all the way at this point right here, so it momentarily comes to a stop before it turns and goes around the other way. I hope that makes sense. Could be a little bit confusing if you want to watch it again, or we'll do more example problems and it'll make a little bit more sense. All right, moving on. All right, so here's formulas to know. We kind of already did the period formula, so we learned about period is equal to how long it takes to make one cycle, right? How long for one full cycle. And when it comes to frequency is just the inverse of that. How many times it can oscillate in that full cycle. Okay? How many times it oscillates in 1 second. Okay, angular frequency, for now you can kind of think about this as like the speed, how fast it's going, but it's a little bit different than that, but that's how you can think about it for now. And this is like the Hooke's law, force of the spring is equal to the spring constant, how stiff the spring is, times how far it is from the equilibrium position. Okay? All right, moving on. All right, for each part, draw the position of an object oscillating horizontally in relation to the equilibrium point and the amplitudes. So this over here says the velocity is greater than 0, meaning it's going to the right. And the acceleration is greater than 0, meaning it's also going to the right. Okay, so what does this mean? So in order for the acceleration to be going to the right, that means it needs to be between this negative a part and this part over here. Because at all this part, the force and the acceleration is going to be going to the right. Okay? So what this is meaning is this is going to look like this. Okay? Here's the equilibrium position. It's moving to the right. Okay? And the force of the spring is pushing it to the right as of now. And accelerating to the right. Okay? Pause it if you want to see if you could do these other ones. But this one over here, the velocity is greater than 0, meaning it's going to the right. And acceleration is less than 0, meaning it's going to the left. If it's less than 0, that means that it needs to be in this part of the block. Okay? So that means it should be like this. And how is that what's happening? So it's moving in this direction, going to the right. However, it's slowing down, and the spring is trying to pull it back, the force of the spring, and it's accelerating to the left. Okay, so it's moving to the right, it's slow, but it's slowing down. Okay. The velocity is less than 0, meaning it's going to the left, and the acceleration is going to the right. Okay, so hopefully you're kind of getting the feeling of this. If the acceleration is going to the right, that means it's on this part of the equilibrium. And if it's going to the left, that means it's getting pulled back, moving to the left over here. So it's moving this way. All right, velocity going to the left again, acceleration going to the left. Okay, so it should look like this. It's getting pulled this way, the force and acceleration are that way. And it's moving this way at this instant of time. Okay, it's getting pulled back. Velocity is equal to 0, and acceleration is to the left. So this is a little bit different. The velocity is only 0 at the amplitude. So it's either on this amplitude or it's on this amplitude. However, if acceleration is less than 0, meaning it's going to the left, that means it has to be on this side. Okay, because this is where the force and acceleration is going to be. So it's going to look like that. It is at the amplitude. All right, in this case, velocity is greater than 0, meaning this is going to the right, and acceleration is equal to 0. When acceleration is equal to 0, what that means is it is at the equilibrium point over here. This is where force and acceleration is equal to 0. So it's going like this, and it's moving to the right. Hope that makes sense. Moving on. Okay, so let's look at this. If it takes 30 seconds for an object to oscillate 5 times, what is A, the period of the motion, and B, the frequency of the motion? So remember, period is equal to how long it takes to make one cycle. So if it takes 30 seconds to make 5 cycles, we could do 30 divided by 5, and we get 6 seconds. Okay? And when we want to find the frequency, remember that's just the inverse. Frequency is going to be 1 over t, which is equal to 1 divided by 6, which is going to give us 0.17 hertz. But what does this this frequency mean? I feel like period makes sense, how long it takes to make one cycle, one full cycle. But frequency is how many cycles happen in 1 second. So in 1 second, how many cycles did it make? 0.17. So this one isn't going very fast, but sometimes things oscillate very quickly. So maybe it can go 500 times, oscillate 500 times in 1 second. This one didn't even oscillate one time in 1 second. It oscillated 0.17 times. Okay, I hope that makes sense. I'm going to keep talking about this later on. Okay, moving on. An ultrasonic transducer used for medical diagnosis oscillates at 6.7 times 10 to the power of 6 hertz. See, this thing oscillates very quickly. So, very quickly. How long does each oscillation take, and what is the angular frequency? Okay. So how long does each oscillation take? That's looking for the period now. And remember, period is the opposite of the frequency, or I should say the inverse. So I could do 1 divided by 6.7 times 10 to the 6. And let's see what this gives us. My calculator. Perfect. And we get, 1, 2, 3, 4, 5, 6, 7. I got 1.49 times 10 to the negative 7 seconds. Okay, it's oscillating so quickly that it makes one full oscillation in this amount of time. And remember, the angular frequency is equal to 2 pi frequency. So it's going to be 2 pi times 6.7 times 10 to the power of 6. And this will be, really big number. Let's see, 1, 2, 3, 4, 5, 6, 7. Yep. 4.21 times 10 to the power of 7 radians per second. Okay. Hope that all made sense. I'm going to be moving on. So this is like a lot of times with medical devices, they use like these vibrations and sounds to oscillate back and forth really, really quickly to find locations of certain things. Anyway, that's a little past you. Let's move on. The tip of a tuning fork goes through 440 complete vibrations in 0.5 seconds. Find the angular frequency and the period of motion. Okay. So this is a little bit interesting. So we know in 0.5 seconds, it's going to complete 440 complete vibrations. So we want to know how long is it going to take to make one complete motion. So now I could do t is equal to 0.5 divided by 440. So this is going to give us, let's see, 1.14 times 10 to the 1, 2, 3. Okay. Negative 3 seconds. So again, oscillating very, very quickly. And the frequency is going to give us is 1 over the period. So this is going to be the inverse of that. Sorry. We're not looking for frequency. We're looking for angular frequency. But anyway, we're going to find it. This. So this is 880 hertz. So what this is telling us is in 1 second, this thing vibrates 880 times. Okay, and that should make sense because if it vibrates 440 times in 0.5 seconds, in 1 second, it's going to be double that. But anyway, the angular frequency is going to be equal to 2 pi times frequency, which is equal to 2 pi times 880, which, let's calculate that. 5,529.2 radians per second. Okay? Hope that made sense. Moving on. A little demo talking a little bit about resonance, which we haven't talked about, but it's a pretty cool video, so suggest watching it. And that's pretty much it. Next time we're going to talk about simple harmonic motion and more with energy. So look forward to watching that, seeing that with you guys. Thanks, guys. Bye.